Well, good afternoon, everybody, and welcome to the first of a series of lectures that we will be presenting here in this auditorium in concert with the exhibition in this museum on Chasing Venus, observing the transits of Venus from 1631 to 2004. We'll have 5 lectures in this series, every other Thursday starting today at noon. And for our first lecture, we're actually, appropriately enough, starting with a talk about the first observation of a transit of Venus and the young fellow who did that back a few hundred years ago. For this, we have invited Wilbur Applebaum to talk to us about Jeremiah Horrocks. And just tell you briefly about Wilbur. He is Professor Emeritus at the Illinois Institute of Technology, quite an expert on the scientific revolution and on the history of astronomy of this period. Definitely, if you look through his list of publications, you see articles about the big names, Galileo, Copernicus, Kepler. He's even the editor of the Encyclopedia of the Scientific Revolution. Well, he's been working on Jeremiah Horrocks quite a bit. He is on his final draft, or working on a translation of the final draft of Horrocks' manuscript of Venus Seen on the Sun. And he is in the midst of producing the first full-length biography of Jeremiah Horrocks. It'll be called Jeremiah Horrocks and the New Astronomy, and we look forward to that in a year or 2, 3 or so, but he's working hard on it, believe me, and it'll be a great publication. So without any further ado, I'll go ahead and ask Wilbur to tell us all about the first observation of a transit of Venus, Jeremiah Horrocks and the New Astronomy.
Somebody stole my text.
Oh, that's me.
I wish I had. Can I be heard okay from here? Is that all right? In light of the impending transit of Venus, it seems fitting to explore some of the circumstances surrounding the first prediction and observation of this rare astronomical event. That this observation was made by Jeremiah Horrocks is in the early 17th century is well known. But before proceeding to an account of that observation, I should like to say a few words about the life and activities of this remarkable young astronomer. Jeremiah Horrocks was born in 1618 in Toxteth Park, a small village near Liverpool. It's now been overtaken by Liverpool. Settled in the late 16th century by several Puritan families. Among them was some skilled clock and watchmakers, including very likely Horrocks' father. Young Jeremiah was well educated at the village school and was admitted to Emmanuel College, Cambridge, the Puritan college at the time, as a sizar, and left in 1635. This is what it looked like in the 17th century, though it's a little souped up, sexed up, as the Beeb says, by Christopher Wren, who worked on it shortly after Horrocks died. As a sizar, his tuition was remitted, but he had to serve in the college buttery or kitchen, wait on fellows at table, and act as a servant to a senior fellow. And, well, that's what it looks like today. I don't think it looked like the dining room at Emmanuel. I don't think it looked that way in his time. It was at Cambridge that Horrocks became fascinated with astronomy after reading an astronomical appendix to a popular work on a transatlantic voyage of exploration. He went on to master the fundamentals of astronomy and the requisite mathematics, and read the classic works of Ptolemy, Copernicus, Tycho Brahe, as well as more recent authors. All this without formal instruction or the company of others with similar interests. In 1635, he purchased a copy of Philip van Lansberg astronomical tables that had been recommended in the astronomical appendix referred to a moment ago. Oops. There we go. This is the cover page. At the bottom of it is in his handwriting, Horrocks' handwriting, saying when he acquired it, you know, a particular date in 1635. Note that the title claims the tables to be able accurately to predict celestial positions for all ages. They were alleged to be perpetual tables. Upon his return to Toxteth Park from Cambridge, Horrocks engaged in extensive astronomical observations with instruments he built and purchased. He persistently tried to improve his observational techniques, concerned about the varying rates of atmospheric refraction at different altitudes, the quantity of his instruments, problems associated with the rays of the fixed stars, ocular parallax, to use a term of the day, that is the effect on observed angles by the distance of the eye from the eyepiece of a cross staff, an instrument to measure angles between celestial bodies. He was also concerned about difficulties in the determination of terrestrial longitudes and latitudes and lack of information about the methods used by other astronomers in reports of their observations. It was not long before Horrocks began a correspondence with William Crabtree, who lived near Manchester, not too far away, and the two became friends and collaborators. Crabtree had found similar problems with Landsberg and encouraged Horrocks to examine the astronomical works of Johannes Kepler. By the end of 1637, Horrocks had acquired and studied Kepler's major works and became a convinced Keplerian, a member of what was still a minority within the astronomical community. He fully accepted what Kepler had called a new astronomy, one that was not limited to the prediction of planetary positions alone, as had been the case since antiquity, but united that function with a search for the causes of celestial motions. Horrocks fully accepted what are now called Kepler's laws of planetary motion, elliptical planetary orbits with the sun in one of the foci of each of them, varying speeds of the planets depending on their distance from the sun, and the proportion between the squares of the orbital periods and the cubes of their distances from the sun. Kepler had also improved Copernicus's astronomy, and Horrocks from the beginning had become a Copernican, by having the sun in the center of the system of planets rather than slightly distant from the center, and in the planes of all the orbits as well. Horrocks differed, however, with Kepler's hypothesis of quasi-magnetic forces emitted from the sun as the cause of planetary motion. Horrocks proposed instead mechanical analogies with falling bodies and a conical pendulum. Horrocks's achievements were considerable. They included his improvement of Kepler's astronomical tables, which had been published in 1627, the very best of their day, and their planetary parameters. Horrocks also verified Kepler's third law based on his and Crabtree's observations. He also created the best lunar theory of its time. Observations of and speculations, he also observed and speculated on perturbations in the orbits of Jupiter and Saturn, which he noticed, and also noticed made a significant improvement in the solar parallax. That is the angle at the sun of the radius of the Earth's orbit. And of course, he was the first to predict and observe a transit of Venus. The mean interval between conjunctions of Venus and the sun is, I think, about 584 days, or about 1 3/5 years. After all, the Earth is also moving while Venus in its 235 days to make a circuit. Passages of Venus across the sun's face are rare phenomena, occurring in pairs 8 years apart with alternating periods of 105.5 and 121.5 years between the second of one pair and the first of the next. There have been 2 per century, except for the 20th, since Horrocks. There were then obviously 4 since Horrocks's first observation. Venus transits across different parts of the sun's face in different transits. This year's transit, June 8th, will be across the lower part of the sun, as was the case with Horrocks in 1639. Horrocks's observation of the transit was made in the village of Hoole, Hoole, 20 miles north of Liverpool, where he spent a year beginning in the summer of 1639. It was long assumed that Horrocks went to Hoole to officiate as a curate. There is a substantial literature on the subject. This myth seems to have originated in the early 18th century, for there are no references in the 17th century to his having been in orders. Horrocks was not even a deacon, much less a curate or reader in Hoole Church. He was possibly a tutor or reader to the most prominent family in the village. Turning now to Horrocks's account of his observation, entitled Venus in Sole Visa. I won't read the rest of the Latin, but the translates as Venus seen on the sun, or an astronomical treatise of a most noble conjunction of Venus and the sun, November 24th, 1639. Since England was then on the Julian calendar, on the Gregorian in use today, that would have been December 4th. The title is taken from the account by Pierre Gassendi, an important French scientist of the time, who had observed the transit of Mercury of 1631. And the title is quite similar, Mercurius in Sole Visas, published in 1632. Horrocks's knowledge of this work appears to have been based not on his own reading, but on the responses to it by Wilhelm Schickard, who had been a friend of Kepler's, in a work published later that year, that is in 1632. Relating how he came to discover the impending transit, Horrocks notes that in checking his data derived from the so-called perpetual tables of Landsberg in early October 1639, they indicated that one would occur the following month. The surprising thing is that neither Landsberg nor anyone else seems to have noticed this. Moreover, Kepler had not expected one until the 18th century. Examining his corrections of Kepler's Rudolphine tables, Horrocks was led to the conclusion that Kepler had erred in the latitude of Venus, thereby failing to predict that it would pass over the face of the sun. But Kepler was closer to the time of conjunction of the planet with the sun than was Landsberg. Horrocks immediately wrote to Crabtree, quote, I have written you to notify you that there will be a notable conjunction of the sun and Venus, November 24th, at which time Venus will transit the sun, which certainly has not happened for many years, nor will be again in this century. I therefore beg you most earnestly to observe diligently with the telescope and to make whatever observations you can, especially of the diameter of Venus, which according to Kepler is 7 arc minutes, according to Landsberg 11 minutes, according to my proportion scarcely more than 1 minute, end quote. He also asked his brother to observe and urged Crabtree to write to Samuel Foster, a professor of astronomy in London, about the impending transit. Horrocks's preparation for the transit was based on what he had read in Kepler, in Schickard on Gassendi's observation of the Mercury transit of 1631, and an earlier work by Gassendi, as well as his own experience. Kepler's recommendation of the use of a pinhole for observation of the diameter of the sun or its eclipses because of its freedom from refractive distortion was rejected by Horrocks for several reasons. It would yield a very small image, not usefully divisible, unless it were a very great distance from the screen, and the very rapid motion of the sun would be difficult to follow with a steady hand. Moreover, owing to the unexpectedly small image of Mercury when it was seen in 1631, it had failed Schickard and another observer because they used a pinhole. Horrocks therefore eagerly turned to the Galilean telescope he had recently bought. Oh, if one could buy a telescope for 2.5 shillings. Horrocks's observation of the was most likely made from his room in Carr House, the home of his well-to-do, likely employer. And there it is. We're reasonably sure it was made from this window. And, well, here's the whole thing. It's a photograph I took many years ago, and this is reproduced elsewhere. But that's most likely from the latitude and longitude Horrocks gave, that's exactly where it was. In a darkened room, the telescope's eyepiece was placed somewhere between 4 to 6 feet from the screen. We can't be sure. In a letter referring to an impending conjunction of Mercury with the sun that he wrote in September of 1638, Horrocks wrote he intends to attach his telescope to an, quote, oblong stick carrying a plane surface at right angles to itself on which to receive the sun's image, end quote. A circle is to be described on the plane's surface, divided, as was later mentioned in his treatise, into 360 degrees, and, quote, its semi-diameter into 15 minutes or any number preferred, and with an index, that was his term, movable around the center. By means of a plumb line, the diameter will be kept in the same position as the horizon, and with the movable index, I'm quoting here, sorry, I will be able to measure the distance both from the center and the top, end quote. His telescope had a probable magnifying power of 10 to 12 diameters and cast an inverted image of the sun about 5.5 inches in diameter on a white screen. In the course of the transit, the apparent distance between the centers of the sun and Venus were compared to the diameter of the solar disk as projected. The end of the telescope with the screen was placed on a movable support so that it could be adjusted as required by the apparent motion of the sun. This method had been described by Gassendi for his observation of the solar eclipse of 1621, a work that Horrocks had read. Horrocks also said that he used an accurate clock and had checked his timepiece against the heavens before the observation. The great disagreement among astronomers on the time of conjunction led Horrocks to begin his observations 2 days before he expected it. On the 24th of November, after being called away for various duties, it was a Sunday, it may have been religious, clearly religious duties of some kind, he finally saw Venus at 3:35 as a circular black spot fully entered upon the sun's disk. This is an imagined illustration by Eyre Crow, a 19th century artist. This is not, of course, the setup as I just described it, and of course he has what Crow presumes is Horrocks's gear as a Puritan. but anyway, that's somewhat what it looked like. That the observational technique was well known before Horrocks employed it may be seen in this illustration of sunspot observations made by the astronomer Christoph Scheiner just a few years before the transit. here we see sunlight coming through the telescope, and there's a figure, that's Shiner, but here he has an assistant, if you notice, actually taking the measurements on the circle of the sun's disk. Horrocks immediately measured Venus's distance from the bottom of the sun and from its center, and again at 3:35 and 3:45, just before sunset. The actual time of conjunction was 6:25 in universal time, with a first contact at 4 minutes to 3 at 2:56. On his 30-minute division of the sun's diameter on his screen, Horrocks estimated Venus's diameter as 1 minute 10 seconds of arc. His fairly accurate determination of the latitude of his observation was 53 degrees 41 minutes. His estimate of the longitude from the Canary Islands, however, was off, as he used incorrect figures given by the noted astronomer Tycho Brahe, and also of his incorrect estimate of the number of miles in an equatorial degree. Hindered by clouds at the beginning of the transit, Crabtree, however, was able to observe it near Manchester at 3:35. His observation agreed with Horrocks's. No one else observed the transit. Horrocks was, of course, very interested in the solar parallax. Comparing the horizontal parallax of Venus, half its orbital diameter as seen from the sun, as Copernicus had it, and Tycho Brahe, Tycho's former assistant Longomontanus, Kepler and Landsberg, he found all of them to have it much too large. His own observation made near conjunction found it to be unobservable, and from Kepler's data on Mars as well, he thought that the solar parallax must be less than 1 minute of arc. That is, the angle at the sun of half the diameter. And he concluded that it was about 14 seconds. Quote, "In a plausible conjecture," Horrocks wrote, as to the mean distance of the sun from the earth, agreeing as well with very accurate observations of the heavens, I found it in round numbers at least 15,000 semi-diameters of the earth." End quote. A figure partially based on harmonic considerations, as Kepler had also done, concerning a fixed proportion between the sizes of the planets and their distances from the sun. That figure, 15,000 semi-diameters of the distance of Venus, was substantially greater than believed at the time, and about 2/3 the modern value, a very great improvement to what was commonly thought at the time. Since the sun had set before Venus had reached the midpoint in its passage across the sun, Horrocks calculated that moment as approximately 5:55 p.m. or 2 hours 36 minutes 40 seconds after his first observation of Venus at 3:35. Horrocks then went on to compare the node of Venus, the point at which the planet's orbit intersects the sun's path, as determined by Copernicus, Longomontanus, Kepler, and Landsberg, and found them to vary widely and as much as 45 minutes from his own calculation. Kepler, as usual, he found to err least of all. Horrocks's determination of the duration of the transit was 6 hours 47 minutes, about 22 minutes longer than its actual length. Horrocks then analyzed how other astronomers would have predicted the conjunction. Copernicus was early by 2 days, 4 3/4 hours. Landsberg by 16.5 hours. Longomontanus was too early by a little over a day and a third. Kepler was closest of all in time, if not in latitude, predicting the conjunction too early by 9 3/4 hours. Horrocks's corrected tables led him to a prediction of the transit to within It's astonishing, 2 minutes of it. It's incredible. His observation of the transit enabled Horrocks to make additional corrections to Kepler's tables for Venus and the Sun. He determined Venus's mean motion as slower by 8 minutes per 100 years, a little slightly lower in his own age than in Kepler. He also corrected the eccentricity of Venus, its distance from the Sun, and the inclination of its orbit to the ecliptic, that is, the apparent path of the Sun against the background of the fixed stars. The apparent size of Venus was important for Horrocks, partly for its role in his harmonic hypothesis about the sizes of the planets in relation to their distances from the Sun. The diameter of Venus, as he and Crabtree observed it against the solar diameter of, this is the observed diameter, by the way, not what he had on his chart, 31 minutes 30 seconds, was close to 1 minute diameter of Venus, 1 minute 16 seconds, which differed widely from those of the leading astronomers, both ancient and modern. Horrocks then speculated on possible causes for the great discrepancy between his observations and the speculations of others. He challenged on several grounds assumptions that Mercury, as observed in the transit of 1631, was really larger than it was seen. After observing the transit, Horrocks decided to publish his results. He worked on his manuscript all through 1640, originally intending to finish it before his visit to Crabtree, planned for January 4th. He asked Crabtree to make inquiries about publication possibilities from Crabtree's bookseller, as Horrocks professed himself ignorant as to how to proceed. Horrocks' treatise on the transit is an account of an important astronomical observation, as well as an analysis of and commentary on the nature of astronomy in his day. Its appeal is heightened by the knowledge that a self-trained young man, living far from the centers of scientific activity, stole a march on all the astronomers of his day. While pervaded by a spirit of mathematical precision and scientific ingenuity, it can be read as an intellectual adventure. It is written in a style now completely gone from scientific literature, for it was only after Horrocks' time that scientists began to discard from their scientific writing the expressions of enthusiasm, the digressions, the classical allusions, and the personal comments with which Horrocks' brief work is filled. Horrocks' search for perfection and precision is reflected in his persistent redrafting of the text of his treatise on the Venus and Solar Visa. There are 4 holograph drafts, none completed, among his surviving manuscripts. 2 of them are identical in wording. One of them a very carefully composed and justified, they still use the term printer's fair copy. There are therefore 3 distinct drafts of varying lengths of Horrocks' treatise, with variations in data in each of them for the same elements of the transit. He was a perfectionist. The order of their composition may be determined from internal evidence. The shortest draft, comprising only 12 chapters, was the last written and was never translated until now. I hope to have it published sometime later this year. In a letter to Crabtree dated September 12th, 1640, Horrocks wrote that after improving the divisions of his quadrant, he redetermined Liverpool's latitude as 53 degrees 25 minutes. Quite accurate by modern standards, by the way, and listed it in the shortest draft, whereas one of the other 2 drafts has it at 53 minutes 20 seconds. The third draft does not mention Liverpool's latitude at all. He must therefore have begun the 3rd draft in the fall of 1640, and on December 12th he wrote that he had, quote, changed my Venus in Sole Visa somewhat, end quote. Anyway, that's what it looks like. That's in his handwriting. Thank goodness for that handwriting. I mean, that's the final draft from my copy of it.